This is the first video for Chapter 7, Techniques of Integration. The basic idea in this chapter is to increase the library of functions that we can actually integrate. So at this point, we only have very rudimentary techniques for evaluating integrals, namely, if we see that an integral is one that we know just from the basic list, then we're good, and otherwise we have u substitution. And that's all we have right now. So in this chapter, we will be learning a whole bunch of different techniques for evaluating integrals. And the first of these is integration by parts. So this is a technique for integrating products of functions. And so if you think about products of functions, we have the product rule from the chapter on derivatives. So that says that if I multiply two functions and take their derivative, so I want to compute the derivative of f times g, I have to write that as f prime g plus fg prime. And so if I integrate both sides of that equation, we find that f times g is the integral of f prime times g dx plus the integral of f times g prime dx. So for instance, I can rewrite that as the integral of f prime, let's write it as fg prime dx equals f times g minus the integral of g times f prime dx. So that's just solving for this term. Now, this is actually the formula for integration by parts. It may not look the same as the one you're used to if you've seen this before. So the way that we obtain the standard form for this in terms of u's and v's is by two substitutions. So we set u equal to f, and we set v equal to g. And when we do that, we find that du is f prime times dx, and dv is g prime times dx. And so over here in my formula, here is dv, here is u, here's u, here's v, etc. And so when I make all the changes, we find the formula is the antiderivative of u times dv is the same thing as u times v minus the antiderivative of v times du. And this is the standard formula for integration by parts. And folks have all sorts of different ways for remembering that, of arranging the pieces that we have over here. I'm happy with any form that you want to write down as long as it is mathematically correct. Okay? So, I want to show you an example of a standard integration by parts problem, and then also for us to consider three variations on this problem. So the first example that we'll consider is to compute the antiderivative of the function s times 2 to the s ds. Okay? So this isn't in terms of x, but we can still use integration by parts anytime we have a product of two functions. And notice that this is a product previously, when we saw a product of functions, we would frequently try to do a u substitution. And you can see here that there's not a substitution that will help. And whenever you see a product of functions, this is always the first thing that you should check to see if there's a good u substitution. U substitution, if it works, is your favorite, best technique for evaluating integrals. Here there is no useful substitution, so we're going to try integration by parts. We need to choose a function that's u and a function that's v, and I will choose u equals s, and then the remainder of the pieces from our integral over here. So here's my u, and I will have the remainder of the integrand to be my dv. Now, in order to use the formula for integration by parts, I need to figure out what du is, and I need to figure out what v is. Du is easy. I take the derivative of s with respect to s, so I get ds here. For v, I have to integrate, and we have to remember that the antiderivative of 2 to the s ds involves a 1 over natural log of 2. And notice that I don't put a ds here, and I also don't put a plus c. We'll add a big plus c at the end that will deal with all of the constants that we have. So, rewriting the formula for integration by parts, so I'll have u times v minus the integral, the antiderivative of v times du, and I just plug in the expressions that I have over on the right-hand side. So my u is s, my v is 1 over ln of 2 times 2 to the s, subtract the antiderivative of v, which is 1 over ln of 2, 2 to the s, times du, which is just ds. And this, if you haven't seen this technique before, this may not look like we've made any progress, but when we simplify, I see that the only thing that I have left to do is to find the antiderivative of 2 to the s ds, which I've already done. So we can complete and here I add a big plus c. And there's a little bit of simplification that we can do. We can factor out a 2 to the s, and we can factor out a 1 over ln of 2. And we're left with s minus 1 over ln of 2. Note with integration by parts, as with any other technique of computing antiderivatives, you can always check your answer by computing the derivative of the function that we have in the box and checking that it's equal to the original integrand of the function. I'll leave that to you to check. Now, the first variation on this theme is when there's actually no product. Right? So your basic integration by parts, I want to reiterate this, basic integration by parts, and most of the ones that you'll see out in nature, is when you have a product of functions. However, these three variations that we're going to look at are situations where you can apply them when it's not obvious that it's helpful to apply them. And I want to show you how that works with an example. So I want to integrate the function arctan of 1 over x dx. And you'll notice that this is not a product. At least not in an obvious way. And there's no useful substitution again. So the way that we're going to do this is we're going to use integration by parts with the following u and v options. We're going to let u be that entire function arctan of 1 over x. And we're going to let dv, once you make the choice of u over here, dv is what it has to be. It's the leftover pieces from the integrand. And this seems like a silly thing to do, but we'll see in a moment exactly why it's useful. So we have to figure out what du is. Du is, so the derivative of arctan of stuff is 1 over 1 plus stuff squared. And because this is a chain rule problem, I have to multiply by the derivative of the stuff. And I also have to multiply by dx. So we'll simplify this a little bit. 1 over 1 plus 1 over x squared times the derivative of 1 over x, that's x to the minus 1, so we have minus 1 over x squared for that derivative, and all times dx. I'll multiply those two fractions together and simplify the denominators. We end up with minus 1 over x squared plus 1 dx. And that's our du. V is easier. Coming from the dv expression, we have that v is just x in this case. This is all the scratch work that we have on the side before we can use integration by parts on this function. So now we put in our u and our v and our du and our dv. So we have u times v, so arctan of 1 over x times x minus the antiderivative of v times du. So that's x times negative 1 over x squared plus 1 dx. We'll simplify a little bit. So I have x times arctan 1 over x minus, well, let's see here, let's cancel those two minus signs, so we end up with plus the antiderivative of x over x squared plus 1 dx. Now, we have to evaluate that antiderivative there in order to complete things, but that's one we can do using a substitution. So I'll write that over here on the side. The substitution is going to be, I'll call it w equals x squared plus 1, and then dw is 2x dx. And now we can plug that in just in the piece for the antiderivative that we're trying to compute. So we'll write out the first bit, x times arctan of 1 over x plus, now let's see here, 2x dx, so I have a 1 half here, antiderivative of 1 over w dw, and the antiderivative of 1 over w dw is ln absolute value of w, so we end up with x times arctan 1 over x plus 1/2 ln absolute value of w, so absolute value of x squared plus 1, all plus c. And because x squared plus 1 is always positive, we can drop the absolute values. In order to get the final answer here. So this is the technique that we use sometimes when there's not an obvious way to use integration by parts, but there's also not an obvious u substitution. And you can see in another example like this on, it's around, let's see here, looking in the book, what page is that example on? It's on page 465, example number 2, where they use a similar technique in order to verify the formula, the antiderivative of ln of x dx equals x times ln of x minus x plus c. And this is one that you can either memorize if you want to, or remember how to use integration by parts in order to obtain it. The next variation on the theme for integration by parts is when you do integration by parts twice. And there are a couple of different flavors of this problem. I'm going to show you one of them, and then I'll point to the examples in the book that match up with this one and the other type. So we're going to look at an example of computing the antiderivative of e to the minus theta times cosine 2 theta d theta. So here's a situation where we have a product of functions. If you try any reasonable u substitutions, you'll see that it won't help, and so we're going to try integration by parts. And there's not an obvious choice for which function I should have be my u here and which one I should have for my dv, because if I take the derivative of e to the minus theta, I just keep getting e to the minus thetas with pluses and minuses. Cosine 2 theta, I'm just going to keep getting sine 2 theta, cosine 2 theta with some coefficients in front. So I'm not getting a simplified integral from this technique. But we're going to see how, when we do integration by parts twice, we can actually solve this problem. So we just make a choice for our first iteration of the parts procedure. So we're going to have u be the first function, and then dv will be the remainder. Okay. And when you do this, so my u gives me a du of minus e to the minus theta d theta, and my v, I have to do a little substitution of u equals 2 theta. When you do that, you end up with v being 1/2 sine 2 theta. So this is our first u and v values that we'll use. Let me call this entire integral here I, and we'll see a good reason later for why I do this. So I have I equals, I'm going to use my integration by parts formula, So u times v minus the antiderivative of v du and I'll simplify that a little bit. I missed a 2 theta there on that first sign. Let's fix that. Cancel those minus signs. 1, 2. And now you see this new integral that we have here to compute is very similar to the one that we started with. So it doesn't feel like we've made any progress, but what we're going to see is that this 1/2 is going to make it so we can actually use this in order to figure out what the value for I is. And now the way that we do this is by doing integration by parts one more time, and there's an important choice to make here now. Up above in the first integration by parts, we didn't have such a good choice, and there was no obvious good choice to make, so we just picked this for our u. And what we want to do at the next step is to make the same choice of u. So u is going to be e to the minus theta, and dv is sine 2 theta d theta, because it has to be. And so we'll proceed with integration by parts like we did the first time. Don't forget that minus sign in the expression for v there that we have. Some folks will call this u1 and v1 instead of u and v. We're just going to keep our head straight and not to recognize that that first batch of u's and v's goes for the first iteration, and the second one goes for the next iteration, as we'll see in a minute. So I recopy my first bit, e to the minus theta sine 2 theta minus 1/2 times the entire quantity of what I get from integration by parts here. So now I have my new u times v minus the antiderivative of v du. Do be mindful of all the minus signs that we have here. Notice that there are 3 minus signs in the last term here, so we'll cancel 2 of them. But we still have the 1 minus sign remaining, and we also have the minus sign outside of the brackets. So what we'll do here, remember this is our expression for I, we'll simplify this by multiplying through that negative 1/2. So we have 1/2 e to the minus theta sine 2 theta. Now let's see here. We have minus 1/2 times minus 1/2, so we get plus 1/4 e to the minus theta cosine 2 theta, and we have minus a 1/2, so again plus 1/4 antiderivative of e to the minus theta cos 2 theta d theta. And what the key here is, because we made good choices, that this expression right here is exactly our I that we started with. Okay? And so what we're going to do is solve for I. So we'll do that by rewriting here. So maybe to save myself a little bit of work, I'm going to simplify those first two expressions by factoring out a 1/4 e to the minus theta, and then I'm left with 2 sine 2 theta plus cosine 2 theta, and then the leftover bits are 1/4 I. I'm going to subtract. Before I subtract, let's go back and fix an error that I'm sure many of you noticed. I lost a minus sign, or I added a minus sign here, and that's going to propagate through here, and that's going to affect the signs that we have here as well as here. Apologize for the confusion there. Let's fix that down below. So inside the brackets I have minus cosine 2 theta, and then minus 1/4 I down here. So maybe what I'll do is erase those erroneous signs if I can. See if the so it won't let me erase those signs. So I'll draw. Maybe if I go here, erase. Nope. Okay. So we'll just fix those in red. Minus sign there, minus sign there. So I need to add 1/4 I to both sides of this equation. I plus 1/4 I is 5/4 I, and that's equal to this 1/4 e to the minus theta times the quantity 2 sine 2 theta minus cosine 2 theta. And I multiply both sides by 5/4 to find that I equals 4/5 is what I need to multiply by. Goodness gracious. And now whole thing plus c. And so the 4/5 and the 1/4 cancel to give us a final answer of 1/5 e to the minus theta times 2 sine 2 theta minus cos 2 theta, all plus c. Okay. That's the final answer here. You can see other examples of this in the textbook. Examples 3 and 4 are similar. Before we finish, I want to show you one more theme, one more variation on this theme. And this is the variation where you make a strange substitution that doesn't look like it's going to be helpful at all, and then you use integration by parts. So here I want to consider the following example, which is to compute the antiderivative of sine of ln of x dx. Now it may be here that using the first technique, the variation number 1 technique, that we tried before, that we used previously, will work in order to also evaluate this integral. I want to use the strange substitution method. There's not an obvious substitution that works here, right? Your guess for a substitution would be u equals ln of x, right? But the problem, and this is the same problem that you see in lots of integration by parts examples, is that our du, which is 1 over x dx, does not appear anywhere in a nice form inside the integral. But there's a tiny piece of cleverness that we can do in order to actually put that du over there. And it's like this. The u expression that we have, u equals ln of x, is the same thing, if you want to exponentiate both sides, of saying that x equals e to the u. Or you can that's just the definition of the natural log function. And so over here in my du expression, I can solve for dx, and that's going to be x times du. But we've just found the expression for x, so dx is e to the u du. And so we can put those things, those pieces, into our integral here on the side. We end up with the integral of sine of u times that dx expression, e to the u du. And if you look at this, this is exactly like, not exactly like, but this is one that you can do. So use variation number 2. So this is the one where we do 2 integration by partses, and you find that this integral ends up being 1/2 e to the u times sine u minus cos u all plus c. This antiderivative is actually done exactly, I believe this is example number 3 in the textbook. And so all that remains for us here is to put our expression for u back in here. So we end up with 1/2. Well, e to the u, let's not put ln of x there. Let's remember that e to the u is just x times sine of ln of x minus cosine of ln of x, whole thing plus c. Note that in that second to the last step, I'm not expecting that you have that antiderivative of sine u times e to the u du memorized, that example number 3 computation. If you've got that one memorized, great, but we're not expecting that. The expectation is that in that step you would use variation number 2 to do integration by parts twice in order to evaluate the antiderivative of sine u times e to the u du. This is the end of the lecture for Integration by Parts, Section 7.1.